Alrighty, we are back with a whole new set of nerds. Good morning, period 3 nerds. Somebody said, okay, thanks. Told you, men don't grow up, they just get old. That one's not old yet, but still never going to grow up, apparently. Nerds, all right, anyway. We got easy lesson for you today, straight out of Algebra 1, literally Algebra 1 material, 100%, nothing new. Solving systems of equations in two variables. Please don't spin the rule. See, maybe the ladies don't grow up either. She's over there playing helicopter with the stinking ruler. She'll call you out by name on the video. Anyway, solving systems of two equations with two variables by graphing the least reliable way to solve a system of equations without technology. Why? Because in order for graphing to be a really good way of solving these things, one, you need to be good at graphing. Two, you're going to need a graphing grid. Three, probably most important, you need the answer to be pretty. And what do I mean by pretty? I mean lands on a perfect coordinate cross. Because how are you going to estimate 3.2? Right? You can't. So yeah, it's the least reliable way of solving systems of equations. But it is a very important concept. And the reason why it's an important concept is because any time in your algebra careers that you have ever set two things equal to each other and solved, it was an Algebra 1 standard that you were supposed to understand that literally means that their graphs were going to intersect at a point somewhere. So anytime we say two things are equal to each other, anywhere in mathematics, we're saying there's a point in space where their graphs intersect. Now, straight lines can only work with each other in one of three ways. Way number one looks like this, where your two lines have different slopes, which guarantees they are going to intersect one time somewhere. Two lines, different slopes, they're definitely going to cross. One solution. I know you can't see it, but this is two lines. These two lines happen to be laying on top of each other. They have the same slope and the same y-intercept. Because this is going to be two lines, technically these two lines are equal to each other everywhere. So because they're exact same line, same slope, same y-intercept, they have infinite number of solutions. And the last one that could occur is two lines with the same slope but different y-intercepts. These lines are parallel. No solutions. Parallel lines will never cross in, as far as you know, in mathematics, okay? If you ever wanted to be a superpower nerd and find out when parallel lines can cross, you could look up non-Euclidean geometry, really interesting stuff, but don't worry about it. One solution, different slopes. Same line, infinite solutions. Parallel lines, no solutions. Those are our only three options. This lesson is all about solving by graphing, and you might notice there's a grid down here, but there's not a grid associated with this one. Gee, I wonder why. I wonder what's going to happen. I'll tell you what we're going to do. We're going to pretend we were going to try to graph them. What form, standard form, slope-intercept form, or point-slope, would you like to graph with? Just shout it out. Okay, that wasn't much of a shout as much as it was a whisper, but yes, slope-intercept. Slope-intercept is the easiest one to graph. And just to remind you, that is slope-intercept. So what we want to do is we want to go to both of these equations and we want to get y alone. We get y alone and we'll be able to graph it with our slope and our y-intercept. I'm going to graph in two different colors, so I'll be doing these two equations in two different colors. I am feeling purple and green go well together, and the best two colors on the planet, orange and blue. Go Gators. All right, so that first equation, 2y equals 6x minus 14. I have to get that y alone. I need a volunteer. Someone tell me how to do it. Nick? Yep, we're going to divide everything by 2. Divide, divide, divide. And that'll do it for that one. It gets us to y equals 3x minus 7. Awesome. Do you have a question for me? No, you want to do the next one? All right, let me go ahead and get it written down. It's going to take a little bit more work to get y alone on this one. But Donald, go ahead and get me started. What would you like to do first? Okay, let's subtract 3x from both sides. That's not the only way to do it, but it is a way to do it. Negative y equals negative 3x, positive 7. Donald, finish it up for me. What do I need to do? Divide everything by negative 1. Perfect. So that purple line would be y equals positive 3x, because when you divide two negative numbers, you get a positive, minus 7 and oh. These are the same line. They have the same slope and the same y-intercept. So since they are the same line, the answers are all, infinite solutions. So I would say all real numbers, but we're not going to leave it in words. We're going to use infinite solutions, like Daniel said, in interval notation. So negative infinity to positive infinity, we'll use those infinities that he mentioned. There it is. Be really careful, because when you graph two lines that have different slopes and they have a single solution, that will be an x comma y pair, and it's going to look like interval notation. Just know when you're talking about an interval and when you're talking about a coordinate, okay? Clearly coordinates can never have an infinity in them, right? Right? Yeah, Mr. Ryan? Okay, great. That one's easy, right? Get y alone. Try to graph. Oh, wait, never mind. They're the same line. Don't even bother graphing. On the next one, I gave you a graph. So clearly, we're going to be able to get a solution here. And I guess I'll just keep the pattern, green, purple, and orange, blue. I'll write more orange this time, and I'll let the blue be the work pin. Can I get somebody new? Just tell me how to get this y alone. So easy, Kelsey. What are you going to do? Yeah, we're just going to add 4x to both sides. Life is good when math is easy. That's what students think. I like my math to be challenging. All right, let's go ahead and graph this line. I mean, we have it. We have it, right? It crosses the y-axis at positive 2, and its slope is 4. But all slopes are technically fractions because they need to be a change in y over a change in x. So we'll read it as a 4 over 1. Both those numbers are positive. That's up 4, right 1. It's right there. I'll grab my straight edge. There we go. And just because I need my students to be used to looking for them, I'll throw some arrows on there, reminding you that that means this graph does not stop just because the grid did. I heard another ruler out there, I think, or metal ruler. So be careful on those tables, they're expensive. And green and purple. Let purple be the work pin this time. A little more work this question to get y by itself. Can I get a volunteer? Can you give me a new one? Trenton. All right, we're going to subtract 3x from both sides. It's going to give me 2y equals negative 3x minus 7. And how would you finish that up, sir? Divide everything by 2. Hey, when you guys are graphing straight lines, do you prefer your slopes to be fractions or whole numbers? Or fractions or decimals is what I meant to say. See, isn't that funny how everybody hates fractions unless they have to graph a straight line? Then they want the slope to be a fraction. Okay, I'm going to challenge what you just said. Because what about this y-intercept? Do you want it to be a fraction or a decimal? Strange how you wanted that one to be a decimal. All right. Now, I challenge you to be super duper accurate when your y-intercept is not a pretty grid point. And then use a slope that does go by pretty values. Oh, but that's right, the y-intercept's not on a pretty point, so we're going to have to be trying to be super accurate every single time. Isn't that worrisome? Would you like to see a way around it? You would, wouldn't you? I don't want to try to guesstimate where negative 3.5 is. I don't want to. And I really don't want to have to count down 3, right 2 from a place that I estimated. Because every time I estimate, I could be introducing small amounts of error, right? I'm going to pretend this slope said negative 1.5 over 1. Why, Mr. M? Why would you bother doing that? Let's just say that I started here. Let's say I plotted that number, negative 3.5. Then I went down 1.5 to the right 1. If I go down 1.5 from negative 3.5, so if my pin was here-ish and I went down 1.5, where would I be? Go down 1 1/2. Where would I be, Max? Down, not up. Down. You're going up. Go down. Negative 5. A whole number. Negative 5 and then right 1. That was not an estimate. That is exact. But Mr. M, that's 1 dot. You're right. Now, use the whole numbers of the slope. Down 3, right 2. No estimations necessary. Yes, Kelsey?
I don't understand where you got the 1.5.
That's what 3 divided by 2 is. So I wrote it as a decimal slope and called it over 1 because I realized that if I did that, I wouldn't have to actually use this wonky y-intercept. Instead, I can use 2 perfect dots and then go through them. Do you have to be able to do what I just did? No. You could go down to negative 3.5, which would have been right there, and then go down 3, right 2. 1, 2, 3, 1, 2. And as you can see, all 4 of those are on the same straight line. But using pretty grid dots is not estimating. That's just a trick. It's just a trick. You don't have to know how to do that. I like knowing how to do it, though. And what I'm noticing is a really pretty, what color did I not use? I didn't use, well, I used a little bit of blue, but I don't want to use red on here because it looks like orange. Look at that. I see a perfect intersection happening right there at negative 1 comma negative 2. That is not an interval. That is an XY pair. If you need to remind yourself, just write X comma Y. And just to make sure it worked, I'm going to plug it in real quick. Negative 4 times negative 1 is 4. And 4 plus negative 2 is positive 2. Yeah, we're good here. We're good here. Ta-da. Pretty cool, right? I don't know about you guys, but I'm pretty impressed with myself with that trick. No one taught me that. I saw it by accident. What's that? Yeah, by realizing that those two together would get me back to a whole number. And we're going to do something similar to that on the back as well. A skill that you'll definitely want to have on the back. You'll see. Can I move on, or are there questions about solving this system by graphing? No questions? Then we move on. We flip it over, and we'll go to the back. Yet again, a system of equations with no grid next to it. dead giveaway that we're not going to need to graph in order to see the answers. Also, you've already seen 2 lines that were the same line, so you can probably guess what this one's going to do. But still, let's get it done. Let's see. You know, I'm feeling red and black. I just am. I'm feeling it. Red and black. I love red and black. Some of my favorite 2 colors to put together, other than, of course, the 2 best colors on the planet. Orange, blue. Let's go Gators. But red and black. I'm going to take that first one. And because I think we have all figured out by now how to get y by itself, I'll just go ahead and make this one happen. Just like the very first example we did, and actually the second example we did, I'm just going to have to divide by the number in front of y. Divide by 4. Gets me y equals, might as well reduce this fraction. 6 over 4 reduces to 3 over 2, just dividing the top and bottom by 2. And 16 divided by 4 is 4. There we go. And let's go Gators. What's wrong? What? What's the deal? She figured what out? What problem? Oh. Good job, Melissa. All right. I'm going to subtract 3x from both sides. And I'm going to divide by -2. When you divide 2 negatives, you get a positive. And 20 divided by -2 is -10. And there is absolutely no reason to graph these 2 things because same slope, but different y-intercepts. Same slope and different y-intercepts guarantee that these lines look something like this setup. They're parallel lines. So there are no solutions. Pretty easy, right? Awesome. It also makes me happy that we get a chance to review graphing straight lines. The last one with just to solve this system, before we get to everybody's favorite part of the lesson, the word problems. You might be wondering, I wonder why there's a 4th example. I mean, I've already seen infinite solutions, I've already seen 1 solution, and I've already seen no solutions. What else could we possibly see? Why is there a 4th example is probably what you're thinking. Let's pretend I forgot and find out. You haven't seen a whole lot of this color combination. I'm going to subtract 2x from both sides because I'm trying to get that y value alone. Makes life easier while graphing. And then divide everything by 4. By the way, that is not orange and green because yuck hurricanes. It's red and green because hooray juniper berries? Mint? I don't want to say Christmas because I wouldn't want anybody to think that I was trying to be religious or anything. But holiday season, yay! Yeah.
Cranberry Sprite.
Cranberry Sprite, my man. Yes. Yes. It is Sprite with cranberry. So freaking good. Okay, anyway. Y equals -1/2 x plus 3 because once again we do want to reduce our fractions for our slope. Then the other, now I'm using orange. This is purple though. Oh, okay. So this time my y's are on the right side. So what? No big deal. You're just trying to get the y's alone. I'm going to add 24 to both sides. And I'm also going to write it backwards at the same time. So 3y equals the 6x plus 24. Then divide everything by that 3. Y equals positive 2x plus 8. We're going to graph the green and purple lines now. The green line has a y-intercept of positive 3 and a slope of negative 1 over 2. Please, please, please. Only one of those two numbers is negative. Don't say they're both negative, because you know if they're both negative, that's a positive number. Make one of them negative. I don't care which one you choose. It won't matter. Out of habit, I say the top one is negative, but that's just habit. It doesn't matter. So I'll go down 1, right 2. Because, look, maybe I didn't want to say the top was negative. Maybe I like my tops to be positive. Fine. It would have been up 1, left 2. It doesn't matter. The point is they're still on the same straight line. One of them is negative. Purple line, y-intercept of 8. Slope is a whole number, but we know that the interpretation is over 1. So I can go up 2, right 1, or I could go down 2, left 1. It's not going to make a difference. Either way, I see, color have I not really written in this question? Blue. The solution is right there at negative 2, comma 4. And I'm not even going to double check that answer in my equations because I could just count down 2, left 1, the purple line lands there. And we already did up 1, left 2, the green line lands there. So because both my equations, I can just easily count the slope to that point, we're good to go there. And again, this is an xy. So does anybody know why I included this example in the notes? It's just a review concept. I'm just curious if anybody sees it. What kind of relationship these two lines have. Alyssa?
A vertical. I
Forgot what it's called? Do you need a shout out?
I think it was like vertical line geometry.
You're thinking of vertical angles, but anytime two things cross, you're going to create a set of vertical angles. But, Gavin, there it is. Perpendicular lines. I just wanted the opportunity to review the concept that when two lines have opposite reciprocal slopes, they are perpendicular. I just wanted to review it. Yes, ma'am. Is there ever going to be a system of equations where the answer is not at a pretty point and I ask you to solve by graphing? No, because it's not accurate enough. Now, I will tell you there's going to be questions where I say solve the system of equations. And you could choose the method of what you're pleasing. It won't matter. But if you choose graphing and it's not a pretty answer, you did it to yourself. So why do I even review it? Because it's an important concept that the student understands that when they solve a system of equations, they're literally finding a point in space where graphs intersect. It's the only reason why I even review it, to be honest with you. And my favorite, is this fourth period? It's third period? Cool. Just enough time to do a word problem. Your toilet develops a leak that completely rots the floor of your bathroom. I got the inspiration for this question from my grandparents. I told them a few years ago, like 4 years ago, their toilet was leaking in their guest bathroom. And they called me like a week after I left. And they're like, oh, no, it was dry in there. Well, here's the thing. That's because no one uses it unless I was there. So I was like, no, I'm pretty sure it was wet. No, we checked. It was dry. Okay. I think last year they had to pull the toilet up and have all the subfloor replaced because it had leaked and rotted the entire subfloor. It's like, oh, it's too bad someone didn't tell you about that a few years ago, huh? Anyway, your toilet develops a leak that completely rots the floor of your bathroom. In order to get it fixed, you start shopping around with a couple different contractors, and I want you to know I had fun coming up with these names. Pete's Pipeworks says that the materials will cost you $1,200, and he charges $75 an hour per hour for labor. Whereas Bob's Baños, well, he tells you that the materials are only going to cost you $800. He must have a deal somewhere. However, he's a pricey guy. He's going to charge $125 per hour for the labor. What we want to know is how long would it take before they cost the same price? And the reason why we want to know that is because we would want to ask them, how long do you think this job will take you? So we could estimate how much it's going to cost and we can determine which one to go with. And the answer would be whichever one was cheaper. So how are we going to do it? We are going to write two equations, one for Pete's, one for Bob's. We're going to graph them, and yeah, buddy. Okay. Pete's will be purple because purple starts with a P. Pete's Pipeworks, he's going to charge you $1,200 for materials. If he works extra long, does the price of the materials change? No. So then what part of slope-intercept form would be the part that doesn't change over time? We have in the slope-intercept form. Which one? Trenton? The y-intercept. The y-intercept is the y-intercept. Pete could show up and go, here's your pipes, I'm out. And I'm still paying $1,200 to this man. My line represents the price going up as time goes up. So the $1,200 is the price when he walks through the door. So then what's the slope? What's his slope? 75. You know what the dead giveaway was that it was a slope? Per. Per means rate. Rate of change. Slope. You see per, it's a slope. So Pete is charging us $75 per hour plus $1,200. Let's plot Pete. That's a lot of P's. We start at $1,200 and then we go up 75 right one. Oh crap. My y-axis doesn't go by 75s, it goes by hundreds. What am I going to do? Trenton, you have an idea? So multiply it by numbers until we get to something that's 100, right? All right, let's multiply it by 2 on the top and bottom. That got us 150. Well, no, not quite. Take this, multiply it by 3. 225 over 3. Crap, 225. Oh, we need hundreds. 75 over 1 times 4. 300 over 4. Bingo. We could say that Pete's slope is 300 over 4. So it's just like me manipulating that 3 over 2, just in reverse. I'm going to call this 300 over 4, and I'm going to go up 3, right 4. 1, 2, 3, 1, 2, 3, 4. There is the next thing. Repeats, and I will use my straight edge to draw his price line. There we go. And we're going to use the same trick for Bob's Baños. Necesito ser baño. All right. What color? Blue. Blue feels good for baños. Blue, baños. Same setup. His per is his slope. So 125x, and he's only charging $800 for materials. Go to 800, and then go up 125 by, darn it. I can't go up 125 easily at least. So what can I multiply my 125? I can multiply it by 4. Good. So my 125 over 1 can be multiplied by 4 on the top and bottom. I forgot to write the 4s. And get 500 over 4. So he'll go up 5. 1, 2, 3, 4, 5. And then to the right, 4. 1, 2, 3, 4. And we will draw his price line. If I could pick up this metal straight edge. And the question was, how many hours would it be before they cost the same? I'm seeing it happen right there. I can also see the cost. Yes, Seeger?
Instead of graphing that, can't you just set 75x plus 1200?
Yes, but that's not solving by graphing. But yes. I want you to do it this way, though, for a reason. So, same cost, which happens to be $1,800 after 8 hours of work. Y'all nerds be packing up early. What's wrong with you? I'm still talking.